For this video, I want to go through some of the problems from the tutorial exercise I asked you guys to do, which is titled as Star Formation and Lifetimes. Before I go over some of the questions, I would like to again review some of the most important things we talked about from last class related to this tutorial exercise. So again, this tutorial exercise emphasizes that stars, begin life as a nebula, and the birth of star begins when a disturbance, such as a shock wave from a supernova, triggers the cloud of gas and dust to spin and collapse inward. And when it collapsing, it's because of due to gravitational attraction. The inward collapse of material causes the center of the protostar to become very hot and dense. Once the temperature and the density reaches some level, and nuclear fusion is going to start. During the nuclear fusion, the hydrogen atoms are combined together to form helium atoms. And when this happens, the star is going to emit light. But once these reactions are sustained, which means that the star no longer collapses, and the inward gravitational collapse of material and the outward pressure caused by the energy given off during nuclear fusion reactions, they reached hydrostatic equilibrium, and the star actually becomes a main sequence star. So the first part of this tutorial talks about this whole process. And I think, if you take a look at, please take a look at the solution I posted on the blackboard. It should be okay for you guys to understand it. The second part, I want to talk a little bit more. The second part of this tutorial exercise talks about how mass is going to decide how long the star is going to stay as a main sequence star. As you can see from this table, on this page, for instance, the first star is 0.67 the sun's mass. This star has 45 billion years of main sequence lifetime. On the other hand, if you have a star which is 60 times of sun's mass, it's going to stay as a main sequence star for about 800,000 years. So which tells us the heavier the star is, the shorter it's going to stay as a main sequence star, and because of nuclear reaction rate actually is higher for high mass stars. So that's why number 4, the question is, which live longer, high mass or low mass stars? The answer is low mass stars. Question number 5, the reaction rate is greater for high mass star. So I want to talk a little bit about number 6. So number 6 says, which of the following statements best describes how the lifetimes compare between star A, a star with a mass equal to the sun, and star B, a star with 6 times the mass of the sun. So how can we do this kind of problem? The way we do is we can go back to the table, finding out star A, which is the same mass of the sun, has 10 billion years. Remember, billion is 10 to the 9th. Star B is a star with 6 times the mass of the sun, which has 70 million years lifetime as a main sequence star. So if we do 10 times 10 to the 9th divided by 70 times 10 to the 6th, which will give you 143. So that leads to the choice for the correct answer to be E. Star A will live more than 6 times longer than star B. Explain your reasoning for the choice you made. Lower mass stars live longer. As seen in the table, a star 6 times more massive than the sun has a lifetime that is more than 100 times shorter than the sun's lifetime. So that's question number 6. Question number 7 is very similar to number 6. So again, the star mass, if you can take a look at this slide over here, the stars, the mass of the stars actually, before the stars become main sequence stars, they're going to follow very similar path. But afterwards, okay, how about the life after main sequence stars? Okay, and you will see next chapter we're going to talk about how different stars, they're going to die differently because their masses are very different. So mass indeed is a very important factor which decides how long the star stays a main sequence and how the stars are going to die differently.